Okay, students, today we'll start the class in which we'll discuss the one of the important topic that is related with the dynamic programming. Okay, in which we'll discuss the 01 knapsack problem using dynamic programming. I have also give one of the assignment and the programs implemented programs in design and analysis algorithms lab manual, okay, in which also that particular algorithms are implemented in C and C++ basically, and you have also required to implement this 01 abstract problem using dynamic programming. Okay, and today we'll discuss this thing, and after understanding this, you will just have to go through this code and run this code and implement this code at your own. Okay, and because it is very important. We have already discussed earlier what is basically the 01 knapsack problem, in which we know that we have one of the bag okay, that have a particular capacity, like in that particular diagram, it is showing a bag we have that have a capacity 20 kilograms. Okay, and this is called knapsack. Okay, and some of the items we have outside this bag that have a particular weight like 4 kilogram, 2 kilogram, 4 kilogram, 1 kilogram, 6 kilogram, and 3 kilogram. And each item is associated also one of the profit associated with all the items also means one first item is this item that have a capacity 4 kilogram and a profit associated with this rupees 6 or dollar 6 basically. Okay, so every items have associated with the weight as well as the profit. And another side we have one of the knapsack that have a particular capacity. Like here we have 20 kilograms, and we have to require to fill this knapsack, this bag or knapsack with these items. And uh, in the knapsack problem is saying that we have to require to fill the item with to maximize the profit basically by always see the constraint whether bag is full or not. Okay, so earlier we have discussed knapsack problem by solving the greedy approach. Okay, and here we'll discuss the 01 knapsack problem. Okay, earlier we have solved the fractional knapsack problem basically, and here we are solving the 01 knapsack problem using dynamic programming. Okay, and from here you can easily understand that 01 knapsack problem cannot be solved by the greedy approach. It can only be solved by using the dynamic programming. Okay, and 01 knapsack problem is what? Means we are not allowed to take the fraction part of any of the item. We have to require to take whole item as well. Either it will be include in the knapsack, otherwise it will be discard or ignored completely. Okay, we are not able here to fill the knapsack with the particular item within a fractional part. Okay, okay. While in the greedy approach, where we have solved the fractional knapsack problem, there we have allowed to take the fraction part of the items to fill the knapsack. Okay. So here we have only required to take the item, that is called one, and otherwise we have to require to discard or ignore the item, that is called zero. So due to this reason, it is called 01 knapsack problem. Okay. So let me start with introduce about what is dynamic programming. Dynamic programming is a method for solving optimization problem. Okay, we all are from the mathematical background, so we know that what is basically the optimization problem. We have to find out the optimum solution out of the various uh, mm, available solution basically. Out of these available solution, okay, feasible solution, we have to require to choose the optimum solution to maximize the profit in the case of knapsack problem. Okay, so the idea is in dynamic programming is to compute the solution to sub problems once and store the solution in a table. Okay, so that they can be reused repeatedly later. Okay, as per our need to maximize the profit. Okay, so it is bottom up approach, not top to down approach. Greedy approach is top to down approach, means we are greedy about to take the first that item there which is have a maximum profit. Okay, while here in the dynamic programming, we have a bottom-up approach we are using. Okay, and by using this dynamic programming, we are solving the 0-1 Knapsack problem. Clear? So let me start. This term coined by the Richard Bellman, and who described dynamic programming as the way of solving problems where you need to find the best decision one after another. Okay, so this is all about the dynamic programming. I think you all have to clear what is dynamic programming. It is optimization problem, bottom-up approach, use table and store problems once in stored in and solution in a table, and then they are reused later as per requirement to maximize the profit. Okay. So properties related means when we will apply, where we will be apply the dynamic approach when your problem have these two properties. If your problem have these two properties, then definitely will be applied to find out the optimum solution. Okay. So if your problem have these two properties, and the main properties of problem suggests that given problem can be solved using dynamic programming, and these properties are overlapping sub problems. Overlapping sub problems means one sub problems when we divide the whole problem into sub problems, and all the problems or the sub problems are some of the sub problems are overlap or related. The results are related with on another sub problem, and it is called overlapping sub problem. And if your problem have optimum substructure, okay, optimum sub your problem have optimal substructure, then we will apply the dynamic programming. Means out of these are two, if we have one or more property in our problem, like in 0-1 Knapsack problem, we have overlapping sub problem as well as optimal substructure also. Okay, so we'll apply if your problem have here we have a problem 0-1 Knapsack problem. Okay, so you have to know that when we have the either or both or properties, if your problem have, then definitely will be applied dynamic programming to solve the that particular problem. Okay, so these are the basic steps will be used or required for the dynamic programming approach. The dynamic programming algorithm is designed using the following four steps. Okay, so very first, characterize the structure of an optimal solution. Okay, we just have to characterize the structure of the optimal solution. Okay, very first, we just have to map this problem in the optimal sub solution basically. Then recursively define the value of an optimal solution. And next step, in step number 3, we have to require to compute the value of optimal solution, and then typically in bottom up fashion. Okay, and last one, in the last step, we construct an optimal solution from the computed information. Okay, so these four steps basically will be used in dynamic programming approach. As we have discussed earlier, that divide and conquer approach have a three steps basically that use the three steps basically. Greedy approach use basically 2 to 3 steps to solve the problem. Here, dynamic programming use these 4 steps to solve a particular problem. So these are the some of the application of dynamic programming. Okay, basically some of the problem where we can apply the dynamic programming approach, like matrix chain multiplication. We'll discuss further. Longest common subsequence also we'll discuss. Okay, traveling salesman problem. You already know that particular problem in computer networks. Okay, computer network you use that particular just computer network problem is mapped in salesman problem and solved by using this problem by using the dynamic approach. And right now in that particular lecture we are discussing about the Knapsack problem 0-1 which flavor of the Knapsack problem 0-1 Knapsack problem, not fractional Knapsack problem. Fractional Knapsack problem we have already discussed with the greedy approach, greedy algorithm design technique. Here we are discussing dynamic programming approach, so we will see the 0-1 Knapsack problem. Okay, so one by one in the further class we'll discuss these all these problems and how can the dynamic programming is used to solve. We'll see. Okay, So let's me start with the knapsack 01 knapsack problem. What is basically the 01 knapsack problem? Also called rucksack problem. Sometimes for your examination point of view, you just have to know this terminology also. So very first, given a set S of 10 items, already have uh, we have discussed. With each item I having a particular weight, all the item associated with the weight and particular positive benefit or profit basically. So W of I, the positive weight of ith item, weight of ith item, and B of I, a positive benefit value or a profit of ith item. You just have to keep in your mind all these things up to throughout this lecture, because it is very important to understand these terminology, because you just have to map this problem in mathematical model. So you have to keep in mind what is W of I, that's the positive weight, okay, and B of I, the positive benefit or value or profit also. Goal. What is the goal of 01 abstract problem? Choose the item with maximum total benefit, but with weight at most W. That's per the knapsack problem is specified, weight of the knapsack. Okay, we have to require to choose the item. Means what we have to require. मैं इस तरह से मतलब कि item choose करने that provide maximum benefit and but आपका weight जो होना चाहिए वो at most कितना होना चाहिए knapsack के अंदर जितना capacity का ही item आपने total item select करने that is equals to capital W. Small w of I is equal indicate the weight of item. Capital W indicate the weight of knapsack. Okay, B of I, profit, yeah, value or positive benefit. Okay, so these three abbreviation you know very well. So in this case, we let T denote the set of item we take, and objective is maximize the B of I. I told, okay, so mathematically we can say we have to require to maximize B of I, means maximize the profit after summation. T is denote the set of items that we take in the knapsack. Okay, which item we are taking and the item जो हम ले रहे हैं, okay, उन सब का benefit अगर summation करें हम, that would be maximize. Okay, तो हमने क्या करना है, maximize करना है. Okay, and the constraint is condition क्या है आपके पास में, means what condition we have, the summation of W of I, means each items का जो weight है, that have a summation, their addition should be less than equals to capital W, that is the capacity of the knapsack. Okay, so I think mathematical mapping of 01 knapsack problem is clear in your mind, and we have to require to write now further we have to require to write the algorithm to solve this problem. Basically, this is the problem and this is the mathematical mapping of the 01 knapsack problem. So why not greedy approach we are using here? Some this question maybe arise in your minds. Okay, and sometimes in your examination also this question may be arise. So why we are not apply the greedy approach? Because greedy approach provide the optimal solution to only fractional knapsack. Always keep in mind this thing. Okay, and 01 knapsack cannot be solved by greedy approach. We can solve only fractional knapsack. So it does not ensure an optimal solution to the 01 knapsack. Okay, so let me start to explain why we are not applying the greedy approach with the 01 knapsack problem. Okay, so only we'll can apply the dynamic programming approach for to solve the 01 knapsack. Okay, so let's start. So this example you can easily understand why greedy approach will be not applied. Okay, suppose we have a knapsack that have a capacity 200 kilogram gram, that any of the unit if you want to take. Okay, and items we have, suppose four items we have, okay, in this problem, and each item weight per weight value per weight, means profit per weight we are calculating, and it is equals to, suppose first item have profit per weight is equals to V1 upon W1, means first item का profit per weight, उसके weight को अगर आप divide करेंगे then we will get profit per weight, basically per unit weight, basically that is equals to 12, and first item have the capacity that weight is 50. Similarly, X2 as second items have profit per weight 10 and weight 55. Third item have profit per weight 8 and weight 10. and fourth item have profit per weight 6 and weight 100. Okay, वैल्यू ऑफ ग्रीडी अप्रोच देखिए, बेसिकली ग्रीडी अप्रोच अगर इसको सॉल्व करेगा तो क्या करेगा, वेरी फर्स्ट एज पर एज द नेम इम्प्लाइज ग्रीडी अप्रोच मींस इट ऑलवेज फोकस टू टेक द आइटम दैट हैव अ मैक्सिमम प्रॉफिट पर वेट. ओके, तो वो क्या करेगा, सबसे पहले उसी आइटम को फिल करेगा जिसका वेट क्या है, प्रॉफिट पर वेट कितना है, मींस प्रॉफिट सबसे ज्यादा अभी जो सबसे ज्यादा दिख रहा है वो इसमें आ रहा है फर्स्ट आइटम में, तो वो सबसे पहले फर्स्ट आइटम को पूरा फिल कर दे. ओके, सो 50 into 12, we'll multiply this. Okay, so 50 into 12. Next, maximum profit per weight have the second item, so 55 into 10 whole item we are taking. Next we have 8 into 10 means that have a maximum profit. Okay, so it is equals to value of the greedy. अगर आप find out करते हैं then it is equals to 1230 only. Okay, but optimum solution, what is the optimum solution of this? If we take 8 of 100, okay, clear, means if we take the weight of this like this and 55 into 10, 8 into 10, okay, then we'll get a profit. I think here we have a 12, okay, that 10 we have. Okay, so greedy approach does not ensure an optimal solution to the 0 1 Knapsack problem because it optimal solution have the solution 1430. Clear? Weight per pound now, okay, we are calculating weight per pound, so it is equals to 600 and then 55 into 10 and 8 into 10, that is equals to 1430. Okay, to solve 0 1 Knapsack, dynamic programming approach is required. Okay, so next, recursive formula for sub problems. What we have, so there are three cases we have in the recursive formula for this particular subproblem. So there are no item in the knapsack or weight of the knapsack is 0, the benefit is equals to 0. Means if one case is there, when we are selecting the item, if there are no item in the knapsack or weight of the knapsack is 0, the benefit is equals to 0. The weight of the item I exceed the weight W of the knapsack minus item of I cannot be included in the knapsack, and the maximum benefit is what? V of I minus 1 or W. Okay, the previous item जो है आपका ith item के साथ में उसका आप वैल्यू बेनिफिट लेके चलेंगे. Okay, उसको इंक्लूड करें. Maximum benefit is that. Otherwise, the third case is the benefit is maximum achieved by either not including item, for example, I minus 1, V of I minus 1 W, or by including item V of I minus 1 uh, or W minus W of I plus P of I. Okay, so there are these three cases we have, and this is mathematically represent these three cases are represented by using this mathematical formula. Case form, conditional form. V of I W is equals to 0. Okay, when for we have first for I equals to 0 or W is equals to 0. Okay, V of I W is equals to second one V of I minus 1 or W when if we W of I is greater than W. Always you just have to keep or write down this thing because in the algorithm we will use these three conditions. Okay, next, maximum, if the third condition, if we have maximum of V I minus 1 W or V of I minus 1 W minus WI plus VI, if we have maximum of these we have, then otherwise we have to use these things. Okay, so these three cases either we include or either we not include the items. Okay, so 0 1 knapsack problem algorithms is what? Let's start with the 0 1 knapsack problem algorithms. For W is equals to 0 to maximum capacity of the knapsack. Initialize first row to zeros. All the actually I told earlier na, because dynamic programming use the table to solve the problem and solve the recursively the problem basically. Okay, so first row all the content zeros, initialization is there, and for I equals to 1 to n, initialize first column to zeros. Okay, V of I of 0 is equals to 0. This is one is the initialization very first. Actually, in every algorithm we will we have a certain steps. So first we have initialization and variable declaration. Okay, so after variable declaration, we are just initialize our table. So initially, our first row, all the first row, all the elements contain 0. All the elements in the first column contain 0. Okay, and then for I equals to 10 and 4, W small w is equals to 0 to capital W up to the capacity. If these three condition will check, okay. If W of I is less than equals to W, means item I can be a part of the solution. Means when W of I is less than ith item is less than the current value of the snapshot, okay, then and after that, if there are the two condition we have, if B of I plus B of I is what? The profit the given in the basically the knapsack. B of I plus V of I minus 1 W minus W of I greater than V of I minus 1 W. This one is the first case that is specified here. Okay. And V IW is equals to then V IW is equals to what? That is as per the this formula, V of IW is equals to V of I plus V I minus 1 and W minus WI. Okay. Else, if this condition is not there, means if this condition is not there, then what is the value of V of IW? If this condition is there, then the V of the IW contain the value of this. If this condition is not, then else part means else part contain V of IW contain V of I minus 1 W. Okay. And if this condition is not, means item I can be a part of the solution. If it is not a part of the solution, then else V of IW is equals to V I minus 1 W. Okay, means what is the meaning of this? Means if item can not be part of the solution, why? Because W of I is greater than the capacity of the current knapsack capacity. Okay, then definitely will not include that particular item, but we have to require to update V of IW that contain the value Vi minus 1 W. Okay, because it is a dynamic programming. It use the current value and the future computation to recursively solve the algorithms. Okay, so these three conditions will be used, and from this we will decide which item can be a part. It's not provide the solution; it just give the solution. Can be a part of the our optimal solution, and which item first we are filter which item I can be a part of the solution and which item I cannot be a part of the solution by using these three conditions. And very first we are initialization, we are performing, and first row contain 0, first column all the element contain 0. Okay, let's run the algorithm on following data. Suppose n contain 4, means total number of elements item we have 4. Weight of the maximum weight of the knapsack is 5, and element V of IW that IV contain weight benefit. Okay, that is specified here 2, 3, 3, 4, 4, 5, 5, 6. Okay, means first element have weight 2 and benefit associated or profit associated with the first element is 3. Second element have weight 3 and uh, profit associated with the second element is 4. Third element have the weight 4 and profit associated with this 5. Fourth element have weight 5 and profit associated with the fourth element is 6. And the total capacity of the knapsack is 4. Okay, W capital W is 4. We have means this one is 2 3 is what we have W of means W1 V1, W2 V2, W3 V3, W4 V4. Okay, so these parameter I think all of you have clear. Now I will just fill this table as per the initialization. First column, first row both contain the value 0 as per the initialization. So for W0 to W, V0 W is equals to 0. Okay, okay. And second one, second step, all the columns, first element, all the elements of the first column, I equals to 1 to n. initialize as per the algorithm requirement I0 is equals to 0. Okay, now we'll fill the remaining row and particular part of the that particular matrix. Okay, so item 2 3 we have initially, or in that particular case, I is equals to 1, b of I is equals to 3. Okay, that is specified here now. Weight of this 2, and b of I is equals to 3, that is specified here. Okay, that is given, and w initially that contain weight 1, w minus wi is equals to what it is, minus 1. Okay, because it is we have na w. Okay, so it is equals to 1. So this case, in that particular case, what part of these three cases we are using, means item I cannot be a part of the solution, because v of I w is equals to v of I minus 1 w. Okay, means w of I is greater than w, means that contain a negative value, so we are using else part. Next, here earlier we have this thing, all the things are same, but w is equals to, now we are changing, it is equals because that contain value 2. Okay, so if w of I is less than equals to w of I is less than equals to of w, there yes, this condition is true, so item I can be a part of the solution. Then we'll check if whether this condition is true or not. So this condition, the first condition is true there. It means if b of I plus b I minus 1 w minus w of I is greater than b of I minus 1 w, this case is true in that particular stage. Okay, so this is equals to 3. Okay, and now again in the next step, w is equals to 3, and again we are on that particular condition, first condition, w of I is that is highlighted by the red. Okay, you just focus on the red highlighter, because it show that this condition is true for that particular stage or that particular case. Okay, and here in the right side we are changing the value. Okay, so w of I is less than equals to w. From here you can see w of I is equals to 2 and w is equals to 3. So ultimate definitely w of I is less than equals to uh, w, small w. So item can be a part of the solution. Okay, and which condition is true in that particular case? B of I plus B of I minus 1. First condition is true. Okay, clear. So again what we are doing, B of IW is equals to B of I, this thing will be there. Okay, means this is the value is equals to 3. Okay, you just have to compute this thing after this lecture. If you are confusing with this thing, you just have to, because it is only a simple mathematical addition and subtraction. Okay, next we have w is equals to 4, first condition, and again the first in the if first condition is true, so v of iw is filled in 3. After the computation, this value is equals occurs 3 basically. Okay, and next we have w is equals to 5, again the same condition we have, this condition is true, this condition is true, so we'll compute this thing, and that will come is equals to 3. Okay, so and the next part we just take I is equals to 2. Okay, and I is equals to 2, and bi of is equals to 4. By why 4? Because we are considering the second item that contain the value 4, and weight is equals to 3. Okay, from here you can see why w of I is equals to 3, because it contain the value 2 3. And initially we आपके पास में w is equals to 1, then w minus wi is equals to negative value, then definitely it will be the third case, else part, so it is equals to 0. Okay, next we have w is equals to 2. Okay, and it is equals to again else part. Okay, why? Because again we have a negative value w minus wi, so it is equals to, after the computation, v of iw is equals to v of I minus 1 w, that will become equals to 3. The next step, we have w is equals to 3. Okay, so first condition is true, and this condition is true. Further, this condition is true, so v of iw will compute by using this formula, and that will be occur 4. Okay, and next we have w is equals to 4 here, and so w of I, this condition is true, and this condition is true after the computation the value. Okay, so v of iw will come equals to 4 by using this formula. Okay, clear. And last one, I is equals to, again we are increasing, that is equals to 5. Again this condition is true because it is positive from here. Okay, and this condition is true, and after computation v of iw will get 7. So we'll fill this table in this way, and similarly we'll apply the same algorithm for third item and fourth item. Okay, so finally we'll get this table. Okay, it's only show the which item can be a part of the solution, which item cannot be a part of the solution. Okay, it's only the one part of the dynamic programming. Now, not provide the solution. It's not a solution. It just show the possible optimum, the feasible all possible feasible solution in this approach. Okay. Next, we are done, and the maximum possible value that can be carried in the snapshot is with the benefit of $7 or rupees 7. Okay, maximum is what occurs 7. Okay, so this algorithm find the maximum possible value that can be carried in the knapsack. Okay, the value is V and W, and to know the item that match this value, we need to trace back through the table. Okay, so how to find actual knapsack item? All of the information we need is in table. V and W is the maximum possible value of the item that can be placed in the knapsack. Okay, let I equals to n and k is equals to w. If I of k is not equals to I of minus 1k, then mark the ith item as in the snapshot. Okay, and I contain that value the same. And else I is equals to I minus 1 and assume that ith item is not in the snapshot. Okay, so let's start finding the item, and we trace back this algorithm, and after trace backing this this algorithm will get that initially I is equals to 4 we have, k is equals to 5. Okay, so initially v of I of k and v of I minus k contain the value this one, and I is equals to 3 we have. Okay, and for I equals to 2, and that contain the value 2 basically, and after that we have the value I equals to 1 and k equals to 2. Mark the item I in the knapsack, and I is equals to this one. Okay, so optimal knapsack should contain what item contain 1 and 2 all. Okay, clear. So running time of this algorithm OW, and from here, and repeat that algorithm is repeat n times, so 1 into W. So running time of this algorithm is O and W. Okay, so application of knapsack problem: resource allocation with financial constraint, construction and scoring of heterogeneous test, and selection of capital investment. These are the application of the item. Okay, so if you have any question, you just have to ask in the chat box as well in the WhatsApp group also. Thank you.